Okay, so we are going to study the substitution reactions. How many substitution reactions do you know? How many substitution reactions do you know?
So for straight chain compounds, it's like four.
Okay,
It's like SN1, SN2, SNI, and SN NGP. We learned like SN1 and SN2 properly.
okay. So what other kind of, you said mentioned for straight chain compounds, right? What others have you learned?
There are like four aromatic compounds.
Okay, fine, fine. That is for aromatic compounds. Yeah. For aliphatic compounds, okay, aliphatic saturated compounds, aliphatic saturated compounds, we have mainly four types of substitution reactions. Okay, as you said, they are SN1, SN2, SNI, SN, NGP. Okay, there are further more divisions. Okay, which are of minor importance. Okay, so even among these four, only the SN1 and SN2 are more important. Okay, the other two, they appear in exam very rare. Okay, so we are not going to concentrate about that in this class. Okay, so if you want any further knowledge about these two mechanisms, so you have to study further from your notes itself. So the first SN1 and SN2, so whatever is going to come in exam, that only we are going to discuss. Okay, so I will make a table, okay, which you can make as a short notes, which will be helpful for most of the competitive exams. Okay, so if I divide into SN, one second. Okay. So there are some specific conditions, okay, which favor one or the other mechanism. Okay. We have some conditions which favor one or the other mechanism. So first, just a second. Okay. Okay. First, let us understand that what is the reaction that is happening. The students, please join on time, because if you join late, it will keep disturbing the flow of the class. Okay. So from tomorrow, yeah, whatever the next class is, please join on time. If it is said that class starts on 8, it is going to start at 8. Okay, so don't be late. Okay. So I have an alkyl halide, okay, generally. And in SN1, what happens? The first step is the part where a leaving group is broken from our alkyl part. Okay. So we get a carbocation which is forming as an intermediate, right? So this intermediate again reacts with a nucleophile. So we get a new bond in place of the leaving group. Okay. So here, that in among two steps, the first step is a slow step, and we know that the slow step itself is the rate determining step of that reaction. Correct. And the attack of the nucleophile, since already this carbocation is an unstable species, then attack of nucleophile is quite fast. Okay. So second step is the fast step. So the reaction proceeds through two steps. In a very basic SN1 reaction, the reaction proceeds through two steps, where the first step is the breakage of the carbon and the leaving group bond, okay, which is the rate determining step. And in the second step, attack of nucleophile. This is the basic SN1 reaction. And in case of SN2, so there is no intermediate as shown in the first step. Okay, only thing that is going to form is a transition state where a nucleophile is going to attack from the backside of the alkyl halide and eliminating the leaving group. Okay, so this overall transition state is having a delta negative charge, because the nucleophile is also negatively charged, and the leaving group, it will also be a negatively charged species generally, right? So that's why there will be a delta negative. So overall, this transition state is electron rich in nature. Okay, so that's what is going to happen in the first only step. Only single step is going to be there in the reaction. So the product will be R nucleophile. Okay, so the thing that you have to notice is the nucleophile is going to attack from the back side of the leaving group. Okay, so if the leaving group is on one direction, from its backside, the nucleophile is going to attack. Okay, so this is the basic reaction condition. Okay, so intermediate or transition state. What type of intermediate is formed? In the case of SN1, a carbocation intermediate is going to form always. Always a carbocation intermediate is going to form, okay, which can rearrange. Which can rearrange. Okay, a carbocation is going to form which can rearrange during the reaction. In case of SN2, is there any carbocation?
No, sir.
Okay, no. So no carbocation in case of SN2 reaction. So if no carbocation is present, then rearrangement won't be there. Rearrangement not possible. Okay, so so what about transition states now? Then how many transition states will be there in SN1? How
There
many
is no
transition
transition
states?
state.
One.
There is no transition state.
No, SN2.
In SN1, will there be no transition state?
No, sir, there is no transition state.
Are you sure about it?
I think there should be one.
Yes, sir.
No. Okay, see here. So what are transition states? Actually, transition states are a neutral species, okay, where a simultaneous breaking and formation of bond is happening. Okay, so in such cases where R, okay, there will be a time when complete bond is there. Okay, so there will be a time where the bond starts to break. So our interaction will be there where this bond starts breaking. This is a transition state. Okay, once this transition state is overcome, that means that the bond is completely broken, we get R positive. Okay, this is an intermediate. Okay, so this intermediate again is attacked by a nucleophile. So there will be a time where there is a formation of bond between the alkyl group and the nucleophile, right? So this is again a transition state. So we will name this as, one second, TS2. This is our TS2. This is our TS1. So finally we'll get a product where the bond between the alkyl group and the nucleophile has been completely formed. Okay, so if there is only one intermediate, okay, if there is only one intermediate, then there will be two transition states across that intermediate. Okay, one before that formation of this intermediate, one after the formation of that intermediate. Is it clear? So there are two transition states in a basic SN1 reaction. Got it? Is it clear?
Yes.
Okay. So see here, number of intermediates is 1. Okay, so we'll come back to this data. So in case of SN2, there is transition state, only one transition state. That transition state is, one second. Where R will be attacked by nucleophile and this will be breaking. Okay, and we know that if it is a carbon, if it's a simple carbon, there will be 3 more groups. So let's assume that it's a carbon. This will be intact. One more H will be there. One more H will be there. Right. So here there is a pentavalent transition state. Pentavalent transition state. Okay. Is it clear? And it is electron rich in nature. Electron rich in nature. Why is it electron rich? Again, why is it electron rich?
So because like an electron-rich nucleophile is attaching to a carbon chain, which is for which
Already
an
having
alkyl.
a negatively charged species, right? Exactly.
Yes, sir.
Okay, a negatively charged nucleophile which is electron rich is attacking carbon which already contains an electron rich leaving group, right? So that's why the overall transition state is electron rich in nature. Okay, so now we talked about a basic thing, okay, where a basic very basic reaction is happening. So you saw that when there was one intermediate, when there was only one intermediate, there will be two transition states in case of SN1. Okay. So similarly, if there are two intermediates, there will be three transition states. If there are three intermediates, there will be four transition states. Similarly, if there are n intermediates, there will be how many transition states? How many transition states will be there?
N plus 1.
N plus
N
1.
plus one transition state. Okay, so if there are n number of intermediates, there will be n plus one transition states. Okay, so when there can be different intermediates, so if one intermediate, you understood that carbocation. So how there can be two intermediates then?
Sir, is a methyl shift, like, or just
Yeah,
shifting.
so when, correct, exactly. Okay, when there is any shift or there is any carbocation rearrangement, in that cases, there can be multiple intermediates. Okay, so in that cases, if there are three different carbocations forming, then there will be four transition states in case of SN1. Okay, so this is a very important point. You have to remember this. In case of n number of intermediates, there will be n plus one transition states. Is it clear? Is it clear?
Yes, sir.
In case of
Sir?
SN2, yes.
Sir, in this class, will we only discuss about SN1 and SN2, or will we discuss like for aromatic compounds as well?
We will see about the time. Okay, so if time permits, then we'll do the aromatic compounds as well. Do you want only?
Okay.
Are you guys very much comfortable with SN1 and SN2?
Sir, you can like go a bit faster on SN1 and SN2, and then like just slow down on the aromatic compounds.
Okay. Do all of you agree? If all of you agree about this, then raise your hands. If you think that this SN1 and SN2 part you already know, so if you raise your hands, then I will be able to move faster. Okay, so all of you raise your hands. Right? Okay, so tell me which part do you want?
So like you can like do a fast
Okay.
summary.
Okay, I will do it fast. Okay, fine. Okay, so number of transition states in case of SN2 will be transition states equal to 0, and number of intermediates will be equal to 0. Number of transition states will be equal to
Always one.
always 1. Okay, without any exception. Without any exception. Okay. So what about potential energy diagram? PE diagram of both. Okay. So in case of PE diagram, how do we plot the graph? In y-axis, what do we write? We write potential energy, and in x-axis we write reaction coordinate. Reaction coordinate. Okay. So if this is my reactant, when a transition state is formed, the energy of the system is going to increase. Okay. So once the intermediate is going to form, intermediates are more stable than a transition state. Okay. So energy of system is going to decrease. So once intermediate is formed, again it passes through a transition state. So again the system is going to increase its energy by a small amount. Then when the product forms, it will be decreasing energy. So this is a potential energy diagram of a most basic SN1 reaction. Okay. In case of SN2, we don't get any intermediates. Same potential energy and reaction coordinate. So we will just have a single transition state which will give us the product. Okay. So this is how the potential energy diagram of SN1 and SN2 is going to look. Okay. So now let's see nature of nucleophile.
So I have one doubt.
Okay.
So
The
in
previous slide?
Yes.
Okay.
So like why is the potential energy of the initial one higher than that of the final one?
Initial, the reactant and product you are saying.
Yes, sir.
See, generally, what kind of nucleophile substitute the leaving group? When a newly formed bond is more stronger than the one which is broken, right? The newly formed bond should be stronger than the one which was earlier present, correct?
Yes, sir.
So if a newly formed bond is stronger, then during the formation of this bond, it is going to release more energy. A strong bond releases more energy, correct?
Yes, sir.
So if it released more energy, then system lost more energy. So that's why the system's energy got decreased. Got it?
Yes, sir. Got it.
Okay. So that is the reason. In case of SN1 and SN2, usually product have lesser energy. Okay. Okay. So we are going to continue with. First, let's do degree of alkyl halide. Degree of Rx. In case of SN1, what will be the order for tertiary, secondary, and primary? If I have
So
3 degree,
3 degree.
will be faster than 2 degree, will be faster than 1 degree. And for SN2, opposite,
Other way
1
around.
degree, 2 degree, 3 degree. The reason being, in case of SN2, what is the reason for 1 degree to be faster?
Sir, like steric hindrance.
The steric hindrance. Okay, we know that the opposite direction nucleophile has to attack. If there are more alkyl groups, then it becomes difficult for the nucleophile to attack. Okay, so reason being steric hindrance. So next is nucleophile. Okay, so SN1 reaction, which kind of nucleophiles prefer SN1 reaction? Strong or weak?
Weak.
Weak nucleophiles. Can you give me some examples? Can you give me some examples? Anyone? Fast. H2O is it?
Weak
MeOH.
bases.
Weak bases, right? So almost all polar protic solvents, they act as weak bases. Okay. CH3COH. Okay, this many are enough for now. Okay. Strong nucleophiles prefer SN2 reaction. Can anyone give example?
NaOH.
Okay. MeONA, NaOH, KOH. Okay, all these things. So SH minus, all this. Okay. So degree of alkyl done, nucleophile done. Then what is the other factor that affects the mechanism?
Solvent.
Solvent. Solvent. Which type of solvent prefer SN1 reaction?
Polar group.
Polar protic solvents, they prefer SN1 reaction. Why do they prefer SN1 reaction? Why do they prefer SN1 reaction?
So as to isolate the alkyl group. Sorry, the halide group. Sorry, not alkyl group.
Okay, halide group, what it does to halide group?
So like the water molecules will like surround the halogen halide group and it like
Okay.
isolating away from the reaction.
Correct,
So
correct.
that the
Okay. Okay, correct. So polar protic solvents generally have high dielectric constant. High dielectric constant. Okay. So what do you mean by dielectric constant? Dielectric constant is ability of any solvent to separate opposite charges or separate unlike charges. Okay. So because of this high dielectric constant, what it does is it ionizes the alkyl halide more. Okay. So that's why polar protic solvents, they prefer SN1 reaction. Whereas polar aprotic solvents, they prefer SN2 reaction. Okay. So tell me, can a solvent decide the mechanism of the reaction? If any reaction is going, so if I change the polar protic solvent and to polar aprotic solvent, can it change the path of the reaction?
yes,
Can it change
but
the path
like
of the
it depends also on the nucleophile.
हाँ अभी सुनो ठीक है. So important note, okay, write it down. Solvents can never change the mechanism of the reaction. Change the mechanism of the reaction, but only it can enhance or suppress the rate. Suppress the rate of that reaction. That reaction. Okay. Remember this point, it's a very important point. Okay. Solvent can never change the path of the reaction. So it means that if any alkyl halide and any nucleophile, if they decide that I have to go through SN1 mechanism, okay. So, and if I use polar reparative solvents, polar reparative solvent cannot stop it. It cannot say that no, you cannot go through SN1 mechanism, you have to go through SN2. It can never tell.
It's just prefer
Okay.
to.
If I do that reaction, if based on alkyl halide and nucleophile, if it prefers to go through SN1 reaction, that SN1 reaction will be faster in polar reparative solvent and will be a little bit slower in polar reparative solvent, but still it will go through SN1 only. Okay, so while deciding the reaction mechanism also, in many of the questions you have come across, they will give alkyl halide, they will give nucleophile, and they will give solvent. Okay, so by looking at the solvent first, if you decide the mechanism, polar protein, yeah, so I will do SN1, then it goes wrong. Okay, so solvent is not a deciding factor. It is just tells us that if this reaction will go faster or will go a little bit slower, relatively slower. Okay, so for deciding any reaction mechanism, we have to first look at the degree of alkyl halide, then followed by nucleophile. Okay, so first and the most important factor that affects the rate or decides the mechanism is degree of alkyl halide, then it is nucleophile. Okay, like if, for example, if I take a 3-degree alkyl halide and if I take a strong nucleophile and tell us that you have to go through SN2, will it go through SN2? If I take a 3-degree alkyl halide and I tell a strong nucleophile, and if I say that you have to go through SN2, will it go?
No.
No. Okay, so first factor that affects is हमेशा याद रखो, first factor that affects or decides the mechanism of the reaction is alkyl halide. Okay, so if you cannot decide by alkyl halide, some of the alkyl halides they prefer to undergo SN1 as well, they prefer to undergo SN2 as well. The best example for this is a 2-degree RX. Okay, so this 2-degree RX, it is okay if it goes through SN1 and it's also okay if it goes through SN2. In such cases, we have to go through the nucleophile. Okay, the next factor is nucleophile. Okay, so only 2 factors actually contribute to our deciding mechanism. Okay, so in 99.99% of the questions, these 2 factors are more than enough. Okay, first you have to check degree of alkyl halide, second you have to check nucleophile. Is it clear for everyone?
Yes, sir.
Okay, so we are going to continue what we were doing. Okay, so these were some notes, okay, in between that you have to remember. Okay, what about stereochemistry?
So SN1 will have 2 products:
Okay,
inversion and retention.
is it always true?
Yes.
Is it always true?
So like the ratio like changes.
Okay, so is it always true that in SN1 reaction 2 products form? Is it always true?
Yes, sir.
What if my reactant molecule is optically inactive?
So if it's like
If my
if it's optically inactive, then like it's one thing only.
correct. Okay, so while giving a true or false question, okay, especially it is important when it comes to true or false question. Okay, such questions come, they will directly write that my alkyl halide will always give 2 products if it is going through SN1. Okay, they will ask for true or false. Just by reading the statement, we will think that yes, it should give receiving mixture. So that's why it should be 2 products, but it is not true. Okay, so first thing that they have to mention is if my reactant, if the reactant is optically active, then the product may be racemic mixture. Okay, product may be receiving mixture. That also may be. So when it will be definitely receiving mixture? When reactant contains only one chiral carbon, only one chiral carbon, then racemization is going to pakka occur. Racemization will occur. Okay, so when reactant contains only one chiral center and that is participating in the reaction, then only racemization will occur. Okay, so these points you have to remember. So we keep telling that racemization occurs. So when they ask that which of the following options racemization occurs, we think that जो भी SN1 हो रहा है, everyone will undergo racemization, but that is not true. Okay, if my reactant is initially optically active, then only it can undergo racemization. Okay, so it's an important point that usually we ignore or we forget during the examination. Okay, is it clear?
Sir?
Yes.
So it has been like experimentally derived that like 100% racemization does not like happen.
That also is true. Okay, so 100% racemization won't occur. Inverted product is slightly more than the same whatever configuration initially had that product. Okay, so I can also give a note that during SN1 reaction, 100% resin mixture is not formed. Racemization does not occur. Okay, so what happens then? Inverted product is slightly more than
Major product.
more than what?
Retention product.
Retention product. Okay,
So
so
could you
here
go
also
back to
they
the
can ask,
previous one?
1 second, I will complete this statement and then I'll go back. Is it okay?
Yeah.
Okay, fine. So then if they ask in which case racemization happens to the maximum extent, then racemization is directly proportional to carbocation stability. Okay, so more stable the carbocation that compound is going to give, the faster or the more will racemization occur. Okay, so these 3 points are important in terms of stereochemistry of that reaction. Is it clear? Is this clear?
Yes, sir.
Okay, so here you want to note down.
Done, sir.
Okay, so here I will fill SN2 part. Okay, in SN2 part again same, if the reactant is optically active, okay, the chiral center on which the reaction occurs gets inverted configuration. Okay, so configuration where it gets inverted only on the carbon which is participating in the reaction. Okay, so sometimes what we do is we know that inversion in configuration happen, so all chiral centers we invert the compound. Okay, so that is not true. Only the carbon which is participating in the reaction gets inverted configuration. Okay, is it clear?
Yes, sir.
Okay, so can I move forward?
Yes, sir.
Yes. So number of steps of reaction, how many step reaction SN1 is?
2. Minimum.
According to
Minimum
minimum 2. And what about maximum?
infinite.
N plus 1 again, where N is number of intermediates. Okay, N plus 1 where N is number of intermediates. This is how many steps? A single step always.
So maximum is also 1, no? For S.
Maximum also 1. Yes, maximum also 1. Okay, always single step. Activation energy. Activation energy, which requires higher activation energy for the reaction to occur.
SN1.
No, okay, everyone thinks like that because we need to break a bond. We think that SN1 will require higher activation energy. Okay, that is not true. Okay, since see there are different factors which affect the activation energy, but the simplest one I can explain is, see, in SN1 an intermediate is formed. Okay, so intermediate is generally more stable, so it is giving a stability factor in between that reaction, right? So what it is doing is there will be some stabilizing factor because of that intermediate formation. Okay, so here activation energy of SN1 is comparatively less and activation energy of SN2 is more. Okay, so generally we say that SN1 reaction is faster than SN2. Okay, it is a general term. Okay, SN1 reaction is faster than SN2 is a general observation. Okay, so if a compound can do both, then SN1 will be faster, relatively faster. Okay, because it contains less activation energy. Okay, understood? I can elaborate on that, but the thing is I don't have that much time here. Okay, so just remember this for as a fact for. Okay, one more thing I have was order. What is the order of the reaction?
SN1
So
is
like second order. For SN.
SN1 is
First order.
first order. Okay, so rate will be equal to, rate is directly proportional to concentration of just Rx. Here rate is directly proportional to Rx
and
as well as nucleophile.
nucleophile. Oh, yeah.
Okay, so here order is 2, order is 1. So how do you find the order of the reaction? देखो हमेशा याद रखो, order of the reaction has to be found out only through experimental methods. Okay, or it will again come in chemical kinetics chapter. Okay, but for now only you remember that order can be found out only by experimental methods. Theoretically it is impossible to find order of the reaction. Okay, so remember this part. Okay, so these were some points of SN1 and SN2 reaction. Okay, is it clear?
Yes, sir.
Shall I move forward? Okay. So should we do substitution on aromatic centers, or should we do elimination
Yes.
first? Which one? Elimination first or substitution or aromatic center?
Sir, you can do aromatic first.
Okay, I will do substitution on aromatic center. It is named as SNAR. Okay. Actually, to name, there are 3 different mechanisms by which substitution on aromatic centers can happen. Okay. First one is known as SN2AR, or it is called as ipso substitution. Okay. So what do you mean by ipso?
SN2, yeah.
Ipso, what do you mean by ipso? So if I have a compound like this and X, so what do you mean by, why do we call it as ipso substitution? Anyone knows? Anyone knows why we call it as ipso substitution?
Sir, is it like something related to the para position?
Para and ortho, yeah.
See here, this position is called as ortho, right? This position is called as meta, right or not? This position is called as
Para.
right? This position is called as ipso. This position is called as ipso. Okay, so a leaving group which is on ipso position is going to get substituted in this reaction. That's why we call it as ipso substitution mechanism. Got it? Okay, so the carbon which directly contains any group is called as ipso for that group. It is called as ipso carbon for this group. Is it clear?
Yes, sir.
Yes, sir.
Okay. So first type of mechanism is SN2AR or ipso substitution. Second one is SN1AR. Okay. Third one is, it is not in your syllabus. It is known as Benzene mechanism. Okay. This one has been removed from your syllabus very recently. Okay. So other two are still there. SN2AR and ipso substitution. Okay. So we are going to study a little bit about that. So tell me, if I take an aromatic compound which contains a leaving group, let me take halogen. Okay, so to this, if I add a nucleophile such as OH minus, okay, can this substitute that halide group? Can this substitute that alkyl group?
Sir, no, sir, it's a very hard process.
Why? Reason. What is the reason?
Sir, like because of slight this resonance effect, it has like slight
Correct.
partial double bond character.
Correct. Okay, exactly. So here there will be lone pair. Okay, so one reason being there is partial double bond character. Bond character. Okay, so one reason being this. Can you think of any other reason? So you have done reactions of aromatic rings, right? In 11th, you have done electrophilic aromatic substitution, correct? Have you done electrophilic aromatic substitution? In 11th?
Yes, sir.
So there, what benzene used to act as? It used to act as a nucleophile, yes or no?
Yes, sir.
Yes, तो इसका मतलब क्या है? It is electron rich. If something is electron rich, then only it will be able to give electron. So in electrophilic aromatic substitution, benzene used to give electron, so it is electron rich. Okay, benzene is an electron rich entity because there are six loosely held electrons which is revolving all around the benzene ring. So 6 electrons are making the benzene ring electron rich. Okay, so it is kind of a bit nucleophilic. The benzene ring is a bit nucleophilic, and this OH minus is also nucleophilic. So can there be any reaction between two nucleophiles? Can there be any reaction between two nucleophiles?
No, sir.
No. So that's why the reaction won't proceed easily. Okay, but if we pressurize it, okay, हमने बोला कि जाना ही है तुम्हें, करना ही है. So then it will do at very high temperature, such as if I remember 673 Kelvin something or 623 Kelvin something. Okay, the temperature you can look it from the NCRT. Okay, for competitive exam they will just mention heating. Okay, so they won't mention temperature, but for boards the temperature becomes important. Okay, 623 Kelvin something and 300 atm pressure. If I pressurize it too much, then it is going to happen. Okay, this is going to attack. Okay, so there will be many intermediates, many resonating structures of this molecule. So this breaks like this. OH minus here, this here, this here. So we know that there will be many resonating structures of this. Minus here, this here, this here. This goes here, this comes here. X, OH. So that's double bond here, that's double bond here. Double bond. So now when this comes, tell me which is a better leaving group, OH or X? It's a better leaving group, OH or X? Here I have a halogen, here I have OH. Which one is a better? So here when minus charge is going to attack here, the carbon will start to have 5 bonds, which is impossible. So it has to remove any one. It has to remove X or it has to remove OH. So which one will we remove?
X.
Which one is a better leaving? X. X is a better leaving group, right? X is a halogen and halogens are a lot better leaving group. So that's why it leaves to form this compound. OH minus. Right? We got this. But we got it at what cost? We had to apply so much temperature and so much pressure. Right? So it costs us so much for attaining that much of temperature for such a simple molecule as a product. Right? So substitution has happened, SN2AR has happened, okay, but at what cost? At a very high temperature and pressure. Okay, so this process is known as, it's an industrial process known as Dawes process. Dawes process. Okay, so here I have not written benzene itself is nucleophilic. Okay, I have not written the reason here. Benzene thing itself is nucleophilic in nature. Okay, so now see, I have done the substitution, I have done SN2AR mechanism, but at what cost? Too much expensive cost, where we are obtaining too much temperature and too much pressure, which is very difficult for us. Okay, so what alternate method we can think of is, by two drawbacks are there, right? Or two difficulties are there that we need to overcome. So can I stop the partial double bond character in my compound? No, resonance is going to happen anyway. So I cannot decrease the partial double bond character. But can I make the benzene ring less nucleophilic? Can I make the benzene ring less nucleophilic somehow?
Yes, sir.
Yes. How?
By adding electron inhaling groups.
By adding electron withdrawing groups. Okay. So if I add electron withdrawing groups at ortho and para positions mainly. Okay. Why? I hope you already know, but if you don't know, then also I'm going to explain later. Okay. So if I add electron withdrawing groups across the ortho and para positions, now a nucleophile, if it comes, okay, will it be able to attack much easier as compared to this? Yes or no? Yes, right. So this nucleophile now will be able to attack this side much easier because the benzene ring has now become electrophilic in nature because of this electron withdrawing groups. Okay, so attack will be much faster. So we will substitute nucleophile in place of the halogen. Okay, so this reaction is going to happen even at room temperature. Okay, so which is the best electron withdrawing group we know? Where electron withdrawing group, the best electron withdrawing group we know is NO2.
NO2.
Right? So if it is NO2, then this reaction is going to happen even at room temperature. Okay, so this is what is going to happen in the reaction. So what is the mechanism? So if I look at the mechanism, okay, it's a very lengthy mechanism. You can draw so many resonating structures in that. Okay, I will draw it in a much simpler way. Okay, so if this is my Cl, let us assume that it is Cl and it is NO2. This is NO2. This is NO2. Okay, double bonds, and here I am adding OH minus as a nucleophile. Okay, so as soon as this attacks, okay, there will be formation of intermediate. You know this intermediate? What is the intermediate formed during SN2AR reaction?
No intermediate.
No intermediate.
In
Are you
SN2,
sure about
there's
that?
like no intermediate.
In SN2 it was no intermediate, but in SN2AR there is an intermediate. Okay, where this OH minus is going to attack like this, and this is going to break like this. Okay, so a negative charge will form here on this carbon, right or no? Negative charge will form here, right? When it moves here, right? Yes or no? Yes or no? Am I audible?
Yes, sir.
So tell me, a negative charge is going to form there or not? A negative charge is going to form there or not? My question. See now.
It will form.
Sorry,
It will form.
it will form, right? So OH minus is going to attack and a negative charge is going to form, and this negative charge is going to resonate with this NO2 group. Okay, similarly, it comes here and negative charge will come here at one point and it will resonate with this NO2 group and it will resonate with this NO2 group. Okay, so a negative charge is resonating all over my benzene ring even with these NO2 groups. Okay, so this is an intermediate of the SN2AR reaction. Okay, this is an intermediate known as M complex. This is an intermediate known as M complex or Meisen-Heimers complex. Meisen-Heimers complex. Okay, or it's also called as a carbanion intermediate. Carbanion intermediate. Okay, so this is an intermediate. Okay, so the stability of this intermediate decides the rate of the reaction. Stability of the intermediate decides rate of the reaction. Okay, and this attack of the nucleophile on the benzene ring is the slow step. It is the slow step. Okay, so in the next fast step, what will happen is, so finally when the negative charge comes here, this will come here and this will break like this. So in the fast step, the leaving group is going to be eliminated, forming this product. Okay, so this is a fast step where a leaving group is eliminated from the product. Okay, is it clear for everyone? Did you understand the reaction?
Yes,
What is happening here?
Sir, why do you keep like NO2 only in the ortho and para position?
See, so we know that resonating structures, whatever charge is forming on the ring, it is going to form at alternate carbons, not adjacent carbons. So you have drawn so many resonating structures, right? So only at alternate positions, the negative charge is going to form when you draw the resonating structures. That is, the negative charge is going to come here, the negative charge is going to come here, and the negative charge is going to come here. So when negative charge comes there, then only the nitro groups can show minus M effect. Okay, they show minus M effect only when they are on ortho and para positions. Okay, so when they are on meta position, there is no minus M possible. Minus M is not possible. Okay, if you want to look at the resonating structures in NCRT, a detailed resonating structural diagrams are given. In Halolkins, Halorins chapter, a detailed mechanism is given with each resonating structure drawn. You can look at it once. Okay,
Okay, sir.
is it clear?
Yes, sir.
So only simple explanation is minus M effect of the nitro group or any electron group can only act when they are on ortho and para. Okay, because the negative charge comes on ortho and para positions only during the resonating structure. Okay, is it clear?
Yes, sir.
Okay, any doubts in this reaction? Any doubts, anyone?
So like for like what are the actual reagents used for this reaction?
So in general we use NO2 only. Okay, here NO2 only. Here also NO2. Here also any halogen. Okay, X, and we use NaOH only. Okay, NaOH. In general, we can use NaOMe. We can use cyanide as nucleophile. Okay, we can use different nucleophiles, but NCRT follows NaOH. So it is better if you practice by using NaOH itself as a nucleophile. Okay, so we get the important product.
So
We know
in
this
general,
product.
can we use,
Sorry,
in general, can we use like any strong nucleophile?
any strong nucleophile will do the job. Okay, any strong nucleophile will do the job. So in NCRT, they follow NaOH. Okay. Is it
So then
clear?
also there was like one reaction right where like there was like a salt formed and it's like only stable from 0 to 5 degrees Celsius.
A salt form? Yeah, diazonium
Not
salt.
salt.
There is one. Yeah, diazonium salt. And
Yes,
that
sir.
reaction also I will do. That after this, that only we'll discuss. Okay. It will
Okay,
take
sir.
just 5 minutes. Okay. So do you know it is a very important compound. Do you know the name of this compound? Very important compound. Do you know the name of this compound?
Trinitro.
That is the IUPAC name that you are trying to say. Okay. So name of this compound, the common name of this compound is picric acid. picric acid. Okay, it's very highly, even in with moisture, it shows highly exothermic reaction. Okay, so it is sometimes used as an explosive as well. Okay, not a very strong explosive, but a pretty strong explosive only. Okay, and this is one of the alcohols which is more acidic than carboxylic acids as well. Okay, so you can see that none of the alcohols, they are very much acidic, right? So they are not that much acidic, but this is only alcohol, okay, which is more acidic than carboxylic acids as well. Okay, so this is a very important compound. Okay, picric acid. Okay, at ortho and para positions there should be nitro groups, and on this OH. Okay, it's called as picric acid.
It's explosive.
Yeah, it is a mild explosive. Okay, mild explosive. Is it clear?
So,
Okay. Then we are going to do that mechanism where we form diazonium salt. Okay, which molecule is this? What is the name of this compound?
furan.
Aniline. Okay,
So
furan is
furan
this.
is
This.
okay.
Furan is this molecule. Okay, this is aniline. If there is OCH3 on the molecule, on the benzene ring, it is called as anisole. Okay, so this and these are important. Anisole and aniline are important. Okay, remember these two. This you can forget. Okay, like for now, for this topic. Okay, aniline and anisole are important compounds. Okay, this is called as aniline. Okay, so when aniline reacts with NaNO2 and HCl. Okay, when aniline reacts with NaNO2 and HCl, it forms something known as diazonium salt, N2Cl. It is called as diazonium salt. Okay, so NaNO2 and HCl, it is going to form a diazonium salt, which is stable only at 0 to 5 degrees Celsius. At higher temperature, it will decompose. Okay, this is called as diazotization reaction. This is called as diazotization reaction. It is known as diazotization reaction. Okay, so what we have done, see, replacing any leaving group on benzene is very difficult. Okay, unless it's a very good leaving group. Okay, so what we have done, NH2, is it a good leaving group? No, it's a very, very poor leaving group. But nitrogen is a very good leaving group because it releases a very stable gaseous molecule N2. Okay, which increases the entropy of the system. So it releases N2, so which is a very stable molecule. So N2 is also known as a super leaving group. N2 is a super leaving group. Okay, so what I mean is removing NH2 and substituting any other nucleophile on that position is highly difficult. So for that, what we do is we convert the NH2 into N2Cl, where N2 can release very easily because N2 is a highly stable molecule. Okay, so that's why it is converted into a diazonium salt. Okay, to this, when I add Cu2X2, okay, it is a cuprous salt. Okay, cuprous salt of any halide, then it substitutes that N2Cl into halogen. Okay, where X can be Cl2 or Br2, where X can be Cl2 or Br. What we cannot do is we cannot use cuprous salt for iodide, or also we cannot use cuprous salt for fluorides. Okay, so this is an important thing that you have to remember. Okay, so in place of NaNO2 HCl, okay, these two basically react to give HNO2. Okay, these two basically react to give HNO2. So in exam, in any competitive exam such as KSAT and all, they can give directly HNO2 as well. So you will search for NaNO2 HCl, it won't be there. Only thing that you are going to find is HNO2. Okay, so HNO2 is again not a very stable molecule. So what we do is during the reaction only, by reacting NaNO2 HCl, we form HNO2. Okay, so the reaction of NaNO2 HCl gives HNO2. So the examiner might want to confuse you. So that's why they might give you HNO2 directly as well. Okay, then also you have to do the same reaction. Then also you have to do the same reaction. Is it clear? Is it clear? Did I confuse you?
No, sir. It's clear.
No, it is clear, right? Okay. So then how do we prepare iodide or iodobenzene then? If I cannot use Cl2, F2 or I2, if I cannot use CO2 F2 or CO2 I2, then how can I prepare iodobenzene or fluorobenzene? Okay, so for that we use a separate reagent. Okay, N2Cl will be there. N2Cl is a common thing. Diazonium salt, diazonium salt at 0 to 5 degrees Celsius is a common thing that will be there. Only thing different for iodine is we are going to use NaI. Okay, sodium iodide. So this will introduce iodine into the system. So we got iodobenzene as well. So for fluorine, what we use Bals-Schiemann reaction. We use Bals-Schiemann reaction. This also is very important. Okay, so in Bals-Schiemann, again diazonium salt is the same common N2Cl. Okay, it is the same thing. The only difference that we are going to use is HbF4. It is HbF4. Okay, so it is nothing but it is a combination of HF and BF3. It is nothing but a mixture of hydrogen fluoride and PF3. Okay, so what it does is it gives fluorine in a very controlled manner. It gives fluoride ion in controlled manner. Okay, so generally what happens is the reaction of fluorine is highly reactive. Okay, all reactions of fluorines are highly reactive. So it is difficult to control that reaction. So we cannot stop the reaction when we want. Okay, so that's why it is very difficult to handle that reaction. So what we do is we don't want fluorine to be highly reactive. So this HbF4, what it does, it's F minus concentration, it does not let it increase too much in the solution. Okay, so it gives F minus in a very controlled manner. So what we get is F minus goes and substitutes that N2Cl. So we get fluorobenzene. Okay, so this is the reaction that is going to happen. Okay, so these are some aromatic substitution reactions. Okay, SNAR. Okay, and what about this reaction? The reaction of diazonium salt, okay, with cuprous halides is known as which reaction? You know the name? You know the name? It is known as Sand-Meyer's reaction. Sand-Meyer's reaction. Okay, Sand-Meyer's reaction. Okay, and the fluorination is called the Bals-Schiemann reaction. Okay, both the reactions are very important in terms of JEE, as well as it is important in terms of KSET, as well as it is important in terms of boards as well. So for all the exams, this part is very important part. Okay, is it clear? Is it clear?
Yes, sir.
Yes, sir.
Okay. So any doubts from today's class? Do you want me to discuss any other topic?
Sir, will you like share the notes? Like if
My
I message
handwriting
you?
is pretty bad. Okay, can you understand my
Well-
notes?
Yes, sir.
You can understand it.
Yes, sir.
Do one thing. Those who want my notes, okay, text me personally because very so many groups are there, right? So it will be difficult to send
Sir,
in all
you've
groups.
recorded this class, no?
Yeah, I
we-
have recorded this class.
Where will you upload? Will you upload it?
Yeah, it will be uploaded. I guess Vignesh sir knows. I think he might have informed where it will be uploaded, or else I
Okay.
will tell him to send a notification. Okay,
Okay, sir.
you will be
Thank you.
informed that where you can find it.
Yes, sir. Thank you, sir.
Okay,
Okay.
sir.
So,
Thank you.
is there any doubt from today's class? First, tell me that.
No,
No?
sir.
No doubt.
No
sir.
doubts. Everything was clear.
Yes, sir.
Yes, sir.
Okay. Okay. So keep these notes as a short notes. Okay.
Yes, sir.
Thank you, sir.
Okay. Oh, then you might leave.
Thank you.
Thank you, sir.
Thank you. Harsha. Ashwarthan, Ashwarthan,